My name is Mikhail Panin. I'm a PhD student at Moscow Institute of Physics and Technology, and I'd like to present my talk about temperature dependence of yttrium bismuth calcium 3 ferrum 5012 thin film magnetic properties. The agenda today will be following. Firstly, I will talk in general about yttrium iron garnet thin films and their applications, and will explain their research motivation. Then I'm going to tell you about our sample and methods which were used in experiment and calculations. After it, I will present the results and finally make the conclusions. I will be ready to answer questions after the talk. So let's start. Iron garnet thin films are now in great demand in the area of spintronics and magnonics because of their high Curie temperature, high Faraday effects, mechanical stability, and low Gilbert damping. There are some prospective areas of study, such as hybrids with superconductors, magnetoptics, magnetic field sensors. Also, there are some things about these films that are not clear enough. For example, dopant effects, composition modifications, impurities effects, how to make very thin films with high damping, temperature dependence of magnetic properties, spin orientation transitions. Because temperature dependence of magnetic properties is a less studied area, we can study them, and the results might be helpful for some prospective areas. On this slide, I have shown some possible applications of such films. Spin valves, there was enough information about them in previous talks. Superconducting spin valves, and an example of the device based on Josephson junction. The aims of our research can be formulated as follows: to explore magnetic properties of iron garnets in film, to construct the methods of evaluating magnetic anisotropy constants, and to search for the applications of these methods. Here you can see our sample features. It is LPE-grown on diamagnetic yttrium scandium gallium substrate, and it is 2.1 micron thick. Also, it is it has rare earth-free substrate. This type of substrate allows us to perform VSM measurements without subtraction of the paramagnetic contribution that gadolinium gallium garnet substrate gives. This makes measurements more precise. On the picture, you can see a microscopy image of the sample from both sides. Let's move on to the experimental techniques which were used in our research. Two main techniques are VNA FMR and VSM. VNA FMR was performed in 5 to 300 Kelvins temperature range, and VSM measurements were performed at temperatures up to 2 Kelvins. Broadband FMR was performed at in-plane and out-of-plane configurations in the whole temperature range. The FMR scheme set up photo and coplanar waveguides with the sample on it can be found on the slide. Now I will briefly explain Makina's classical universal methods to evaluate anisotropy constants and germagnetic ratio. It is based on Sewell-Smith-Bellier's approach. Firstly, free energy F is compiled from Zeeman energy, demagnetization energy, and magnetic anisotropy energy. The resonance frequency is found from Soule-Smith-Bellier's formula and expressions for minimizing free energy F. Soule-Smith-Bellier's equation cannot be solved in general case, but in case when the external field is perpendicular to the plane and parallel to the plane, we can write simplified equations. And using the polar angle fit in these simplified equations, we can find first cubic magnetic anisotropy constant, uniaxial magnetic anisotropy constant, and ferromagnetic ratio. Also, I should say that saturation magnetization should be known from direct measurements in this method. Makina's method uses measurements at only one frequency. We suggest to use advantages of broadband FMR to calculate some important values. In out-of-plane orientations, frequency from field dependence has a linear character. We can extract geomagnetic ratio from the slope and effective magnetization from H-axis intercept. This effective magnetization can give us information about the type of anisotropy. If the value is negative, then we have easy axis type of anisotropy, and if it is positive, we have easy plane type of anisotropy. Now it is time for the results. On this slide, you can see geomagnetic ratio and effective magnetization, which were calculated from the linear fit. Geomagnetic ratio varies within the margin of error with temperature. We do not detect significant temperature influence on this characteristic. We can see that effective magnetization is always a positive value. It means that our sample always has easy plane type of anisotropy. On the next slide, you can find VSM measurements, hysteresis loops at different temperatures and temperature dependence of saturation magnetization. Hysteresis loops confirms the easy plane type of anisotropy because the saturation field is high in out-of-plane configuration and low in in-plane configuration. The temperature dependence of saturation magnetization looks similar to other type of iron garnets in films, but has a kink at temperatures lower than 5 kelvins. It is not an experimental mistake. The kink is field dependent, but the nature of this feature needs to be studied deeper. On the next slide, you can see the effective value for PM effective minus saturation magnetization and the first order cubic magnetic anisotropy constant. This effective value demonstrates a linear decrease with temperature, and it means that general anisotropy grows with the decrease of temperature. The absolute value of K1 grows with the decrease of temperature. It is pretty typical behavior for this parameter in iron garnets in films. On the next slide, the uniaxial magnetic anisotropy constant temperature dependence is demonstrated. It has an interesting behavior. If we decrease the temperature, the constant firstly decreases, then has a minima, and then starts to increase, changing the sign from minus to plus near 170, 180 kelvins. In some books, the change of sign of uniaxial anisotropy constant is linked with easy plane easy access transition, but it works only if there are no other anisotropies. In our case, we've seen that there is no such transition. And so we connect this change of sign to growth-induced anisotropy temperature behavior. We have found some similar temperature behavior of growth-induced anisotropy in other types of iron garnets in literature. Full uniaxial anisotropy constant is a sum of growth-induced constant and stress-induced constant. We made some estimates and consider stress-induced constants much smaller than the growth-induced one in our case. These estimates are based on literature information. In the next slides, I will try to explain how our research can be helpful for application. For some devices and heterostructures like those on the slides, when something is placed on our iron garnet on the substrate, it could be useful to know the parameters of the garnet before making a structure of it or based on it. At least the type of anisotropy and where the magnetization is directed. It can be done with our method using FMR quickly. Now it is time to make conclusions. Temperature dependence of thin film magnetic properties was explored. Makina's method of calculating magnetic anisotropy constant was modified. Substrate advantages were discussed. The change of sign of uniaxial anisotropy constant was linked to the growth-induced anisotropy, and the connection of to the low temperature application was discussed. Thank you for your attention. Now I'm ready to answer your questions.
Thank you very much for your talk. Are there any questions from the audience? Yeah. So we have a question from Diana.
Hi, so thank you for your presentation. I have more of a curiosity. So you discussed the importance of these substrates for your films. Is there any possibility of using different substrates where to grow these materials? I imagine that there will be consequences, but is there any viable alternative to these TGD?
Of course, it is even not the most popular substrate, as the most popular substrate is gadolinium gallium garnet, and it has it is paramagnetic, and it has drawbacks because for example, to make VSM measurements using the paramagnetic substrate, our sample, for example, it is 2.1 micron, and the substrate is usually about 500 microns. And when we make measurements of the magnetization, we need somehow take into account this substrate, which is paramagnetic, and this substrate, the part of the substrate into general magnetization, if it's paramagnetic, can be pretty decent.
Okay, thank you.
And our substrate is diamagnetic, and we think that it's better than the gadolinium gallium substrate, which is more popular.
Thank you.
Thank you very much again for